Okay, in this video I'm going to be looking at how we can determine the pH of acids. Now before we do this we need to understand what pH is and how we can find it. So pH is a measure of the concentration of hydrogen ions in an aqueous solution. pH can be calculated by finding the minus log of the H plus ion concentration. Now water will naturally dissociate into H plus ions and hydroxide ions. And since this is an equilibrium process, as long as we don't change the conditions, the concentration of these products is going to remain constant. And we can therefore express this as an equilibrium expression with an equilibrium constant, Kw, equaling the concentration of hydrogen ions times the concentration of hydroxide ions. We can ignore the concentration of water. Since it's an aqueous solution, the water can be assumed to have a constant concentration of 1. Now, under standard conditions, so 25 degrees Celsius, the concentration of H plus ions and OH minus ions in pure water is exactly the same as each other and will have a concentration of 1 times 10 to the minus 7 moles per decimeter cubed. And since these are the same as each other, the Kw value is going to be 1 times 10 to the minus 7 squared, or 1 times 10 to the minus 14. And this essentially gives us the foundation for the pH scale and the reason why the pH scale goes up to 14. Because if we have a concentration of H plus ions of 1 mole per decimeter cubed, in an acid, 1 mole per decimeter cubed, if we take our equation above, the minus log of 1 is 0. So the pH is going to be 0. Now in this situation, the Kw must still be 1 times 10 to the minus 14. So the OH minus ion concentration is going to have to be 1 times 10 to the minus 14 in order to give us a Kw of 1 times 10 to the minus 14. So the OH minus concentration is going to be 1 times 10 to the 14. We can therefore assume a pOH, which is exactly the same as pH except for the hydroxide ions, of 14. Now that gives us the maximum possible concentration of H plus ions in solution. However, if we take hydrogen ion concentration of 1 times 10 to the minus 14 moles per decimeter cubed, i.e. a pH of 14, then the OH minus ion concentration is going to have to be 1 mole per decimeter cubed, because it still must multiply to give us a Kw of 1 times 10 to the minus 14. So the limits of our pH scale are determined by the dissociation of water, and in fact these limits can change if we change the temperature away from 25 degrees Celsius. But if we assume that the temperature is going to be fixed at 25 degrees Celsius, then our pH scale, the maximum concentration of hydrogen ions gives us a pH of 0, and the minimum concentration of hydrogen ions gives us a pH of 14. So this is how we can actually determine pH, and we can use this equation here to find the pH, the hydrogen ion concentration of any solution. So if we have a strong acid, strong acids dissociate fully. So for example, hydrochloric acid will dissociate into H plus ions and chloride ions, and every single molecule of HCl is going to dissociate. Therefore, in the reaction, in the solution, the concentration of H plus ions is going to be the same as the initial concentration of acid. So if we know the concentration of the acid, we can determine the concentration of the H plus ions using this equation here. So pH is the minus log of the H+ ion concentration. Of course, this is assuming that the acid is monoprotic. So we are talking about acids like hydrochloric acid or nitric acid. In sulfuric acid, the first proton, which is dissociated fully. However, the second proton is dissociated partially as a weak acid. So you probably won't have to calculate the pH of a sulfuric acid solution. For standard levels, you need to be able to calculate the pH of strong acids. For weak acids, you can make an assumption at standard level that the concentration of H+ ions in a weak acid is approximately 1% of the initial concentration of acid, since weak acids dissociate partially. This is very much a generalization, and therefore the concentration of H+ ions in the solution of a weak acid is going to be about 1/100th of the concentration of the initial acid. Which will give you a rough estimate of the pH of a weak acid solution. Standard levels, you don't need to be able to do more than that. However, for higher levels, you need to be able to calculate the pH of weak acids. And in order to do this, we can use the weak acid dissociation expression. So weak acids exist in equilibrium, where our weak acid HA will dissociate to produce H+ ions and conjugate base ions A-. The equilibrium expression for this is going to be Ka, so the acid dissociation constant, equals the concentration of the product, so H+ times A-, divided by the concentration of the reagents, which is the HA. Now, there are two assumptions that we can make with weak acids. This is always happening in aqueous solution, and the dissociation is negligible. Okay, so most of the molecules in here will still be on the undissociated side, on the left-hand side of the equation, with a very, very small fraction dissociating to form H+ and A-. So the first assumption that we can make is that the concentration of HA at equilibrium is the same, more or less, as the initial concentration of the weak acid. So in a question, if you're told that you have a 1 mole per decimeter cubed solution of weak acid, you can assume that the concentration of the weak acid at equilibrium is 1 mole per decimeter cubed. So that's our first assumption. The second assumption that we can make is that although this is dissolved in water, and water will be contributing some H+ ions into the solution, the number of H+ ions contributed at equilibrium is going to be negligible, as an increase in concentration of H+ ions due to the acid is going to shift the equilibrium of water over towards the left. So we can assume that the concentration of H+ ions is solely due to the due to the dissociation of the weak acid, and that therefore the concentration of H+ ions is the same as the concentration of conjugate base ions. So H+ and A- will have the same concentration. So we can make these two assumptions, and these two assumptions allow us to rearrange this equation in order to determine the concentration of H+. So since HA and A- are the same, then Ka is going to be equivalent to H+ squared over HA. Now we can simply rearrange this in favour of H+, and say that H+ is going to be equivalent to the square root of HA times Ka. So we can now determine the concentration of H+ ions at equilibrium, and therefore the pH at equilibrium of our weak acid, using the equation as pH is minus log of the H+ concentration. The acid dissociation constant Ka can be obtained from your data book. In the data book you have tables with the pKa values. Now the pKa is related to the Ka in the same way that pH is related to H+. So the pKa is equal to the minus log of the Ka, which means that Ka is equal to 10 times minus pKa, or 10 to the power of minus pKa. So you can determine the Ka using this equation here and from the values in your data booklets. So using this method, we can find the pH of a strong acid, simply using this equation, or the pH of a weak acid by rearranging the acid dissociation expression, finding the Ka value from the data booklet, and then once you have the concentration of H+ ions, again you can use this equation to find the pH of a weak acid.